We have found the Maclaurin series expansion for e to the x. And there it is. X to the n over n factorial, the summation, as n goes from 0 to infinity. Now let's see if we can find the Maclaurin series expansion for sine x. Well, now remember the Maclaurin series expansion goes like this. You've got these terms. The very first term is going to be f of 0, x to 0 over 0 factorial. That's the very first term. Then you got your next term, which is the derivative evaluated at 0, x to the first over 1 factorial. And then you've got the next derivative evaluated at 0, x squared over 2 factorial. You really quickly see a pattern forming here. There's the third derivative evaluated at 0, x to the third over 3 factorial. Then you got the fourth derivative. And we'll do one more, the fifth derivative. And at this point, I think we'll see a nice pattern here. Okay, so we want to simply figure out what each one of these terms are, and then we can get our, we'll say, okay, this is the Maclaurin series expansion for sine. So first of all, I take sine, and I'm just going to plug in a 0. Well, sine of 0 is 0. So on this one, what we've got is we've got sine of 0, x to the 0 over 0 factorial. Well, that's just 0. There's no point in spending any time with that. Now, the first derivative, so the derivative of sine is cosine. So we've got cosine of 0, x to the first over 1 factorial. Cosine of 0 is 1, so this next term is just x. That's all it is, just x. Okay, now let's look at the derivative of cosine, which is negative sine. Negative sine of 0, x to the second over 2 factorial. Well, once again, sine of 0 is 0. Now you can see our derivatives are going back and forth between sine and cosine. Now the derivative of negative sine is negative cosine. So negative cosine of 0, x to the third over 3 factorial. Now cosine of 0 is 1. You got that negative in front, so this is negative x cubed over 3 factorial. So now it looks like we got 4 terms here, 2 of which are non-zero. Now the derivative of negative cosine is going to be sine. So sine of 0, x to the fourth over 4 factorial. Well, once again, that's 0. Now, so every other derivative has sine in it. Sine of 0 is 0. So you can begin to see, all these even terms, all these even powered terms are going to be 0. The only thing I'm going to have are the odd powered terms, x to the first, x to the third, and now x to the fifth. The derivative of sine is cosine. So we've got cosine of 0, x to the fifth over 5 factorial. And you can see that cosine of 0 is 1, so we've got x to the fifth over 5 factorial. And we start to see the pattern here. Notice we have x minus x cubed over 3 factorial. You know, I'm taking out these zeros. And then plus x to the fifth over 5 factorial. And you can see, you know, just looking at the pattern here, it looks like the next term is x to the seventh over 7 factorial, x to the ninth over 9 factorial, minus, you know, and it goes on and on. And what we might want to do is write this in a more compact fashion using summation notation. Now notice this is the Maclaurin series expansion for sine, and notice these are all odd powers. And so here I have an odd polynomial. Now that's not surprising because remember sine is an odd function. So if you look at this, you see, this has just got odd powers in it. So let's see if we can write this using summation notation. Now, first of all, we notice that all the powers of x are odd. And the powers of x match the factorial on the bottom. So let's see if we can write this. I've got a top and a bottom. And how do we write odd powers? Well, 2n plus 1. That's the way, you remember 2n is a way you can represent an even number. 2n plus 1 is a way you can represent an odd number. So I'm going to put 2n plus 1 up there and 2n plus 1 factorial down here. And notice that that will match, let's see if I let n be 0, let n go from 0 to infinity. Let's see if this works out. If I put a 0 in for n, the very first term is just going to be x. Check. Got that. Now let's try it for n equals 1, and let's see if our formula here works. For n equals 1, up here we've got x equals 3, 2n plus 1. If n is 1, this is 3, x to the third. And down here on the bottom, we got 3 factorial. However, it's negative. So I need to put the little trick to having an alternating series, negative 1 raised to a power. I think I need to write this negative 1 raised to the nth power. Notice, if n is 0, negative 1 to the 0 is 1. If n is 1, negative 1 to the first power is negative. What about if n is 2? Well, that would give me a positive again. So it's starting off positive, negative, positive. So this is it. This looks like it will work. And we could try it out more, for some of the other terms. But this right here is the Maclaurin series expansion for sine. Now, what I want to do is I want to look at this graphically. In other words, I want to look at this series graphically and compare it to the graph of sine. So that's what we want to do next. Okay, so notice what I've done. I've put in the first plot here just sine. There's the graph of sine. And then I put in, for this second plot, I put the summation formula that we just found. And I've noticed I've left k up here to be something that I could adjust. I can adjust it with this slider. So I start off with k equaling 0, and what we have is the summation n going from 0 to 0. So really, we just get the very first term of the Maclaurin expansion. And remember, that was just x. X was the first term. And you'll notice I've got the line y equals x right there. Now let me go 2 terms. Okay, so n equals 0, and then k equals 0, and then k equals 1. And notice that now we've got the first 2 terms. And notice the difference. We start off with just a line, and now notice just with that addition of 1 term, the blue graph matches up to sine a lot better. Now if I go to the next term, and notice with each term, our Maclaurin series graph matches up to our graph of sine better and better, right? So look at that. See, here we go. Now notice that 2 pi is a little over 6. So if you just look at between -6 and 6, we have a pretty good match already, and we've just gone out from n equals 0 to n equal to 8. From n equals 0 to 8, that summation. And you can see, we could go on and on. But you can see that as we add more terms, we get a better and better fit. And in fact, if k is infinity, if we let the number of terms go to infinity, well, then this Maclaurin series expansion is the same as the sine.